So before we move into point charge stuff, let's sort of review and summarize what you guys have been doing with parallel plate setups, nice uniform electric fields. So I mean, it kicks back to grade 11, what you guys did in grade 11. Or in grade 11, of course, you had the expression F equals QE. Let's make it a little bigger. F equals QE, and you guys could calculate the forces of charges in electric fields. So you guys find forces doing this, and then what you would often do is you'd use F equals ma to find the acceleration of the charges, and then it was often a combination of the other two classic kinematic expressions to find out different things about the charges going across. There's not much difference between that and what you guys can do now with a little bit of the grade 12 energy ideas, because a lot of it's the same ideas. The only couple slight differences, but it's still typically finding the similar type of quantities just in a different way. Where if the charge goes across, work of course is equal to the force times the distance across the two. Of course, the force is the Q times the E, which is the exact same thing, of course, as this expression from good old grade 11. And then what we sort of did is we sort of changed a little bit. We looked at it a little bit differently because that is the work done. But of course, this would also be the potential energy that the charge would have. It would also be the kinetic energy that it has. So you could use, of course, the kinetic energy to find the speed. So you can do very similar types of things depending on which way you want to look at it, grade 11 way, grade 12 way, or a lot of people use a combination of the two. Really the only new type of quantity that really kicked in for us in the fields type stuff is the whole idea of electric potential. So not electric potential energy, which is often found, QED or something like that, but just electric potential, where if there's no Q in between the plates, there's nothing there. There's just the potential for something to happen. And unless you have something in there, there's nothing to take advantage of the potential and use it as potential energy. So the idea was take that QED expression. We had the, you can have potential energy is equal to QED. Take out that Q, remove the Q from the situation, remove the Q from the formula, and you're left with just electric potential. So electric potential, that was the voltage, was just E times D. And that's why you'll often see this expression written as, instead of QED, V times D, no, not V times D, but Q times V, took the wrong letter there. You'll have to see potential energy especially, or the work done is QV, and of course, this is all the same type thing. It's be equal to all those guys. So that's really the only new quantity that we have is the whole voltage idea. And it's often, you have voltage across plates, and then they tell you what could possibly happen. Okay, and we mentioned this before, but that's why if you've got, your typical household outlet, most people know that there's 120 volts in an outlet. Well, 110 to 120 typically, but it's 120 volts because literally these are literally parallel plates, and the parallel plates are purely there to supply potential, but they're not actually good for anything until you actually plug something in. And when you actually attach something to the actual plates, put something in between the plates, then that potential can be used as potential energy and make things run and make charges move and that type of stuff. Okay, same idea for even just like a regular cell. That's why the quantity typically given on these guys is right there is the voltage. It's the potential difference. So you literally have a metal plate here and a metal plate at the bottom, and those two metal plates, they have electric potential between them. And until you actually attach the battery to something, it's totally useless. It's not until you actually attach that electric potential to something like a circuit, and then that electric potential can then supply electric potential energy. The charges can move and actually do stuff and cause things to actually happen. So really the electric potential, the voltage, is the only real new quantity that we are dealing with in parallel plate setups, aside from the energy, but the energy is something that you guys have taken in your previous mechanics sections. Okay, so it doesn't really matter which way you use to solve questions. You can use the classic F equals ma, vat, dtv. We've incorporated some of your newer formulas, like you can use the distance equals 1/2, at squared and stuff like that. So you can use a lot of that stuff as well. So some people like the more classic forces and kinematics type way to do it. Some people prefer the work and energy way to do it. It really doesn't make any difference. Often the work and energy is a little bit quicker, but it doesn't really matter. You can solve it either way. The only kicker that kicks in is if you have the voltage and you need to use the voltage to find the electric field, because without voltage or without the electric field, the old dynamics kinematics way doesn't work too well. But it doesn't really matter. Based on the information you're given, you can do one way, the other way, or a combination of the two. It doesn't make any difference. You'll end up with the exact same result. Okay, so let's sort of look at that a little bit and sort of show. So let's just take something really, really simple. Let's go with, let's say we've got 5,800 volts attached between two plates, and let's say they are separated by, let's go with 3.4 millimeters apart, and I want to know how fast the charge is going on the other side. And we're going to solve this both ways, more the way grade 11-ish type way, as well as more of energy grade 12-ish type way. And we can do it both ways. Now, the thing is, since I have the voltage and I have the distance, I really don't have much of a choice. I need to find that electric field in order to do it the F equals QE type way. So I'm just going to start by finding my electric field. And of course, the electric field is just going to be that expression right there. So that's just V divided by D. And I can find my electric field. I got the voltage and I've got the distance, and I can divide the two and get my electric field. Okay, so if we do that, we should get about 1.71 times 10 to the 6 newtons per coulomb. And then once I've got that, really I can do it strictly the grade 11 type way from here on in. Now the only thing is, if I'm going to find the speed, I actually need to put something in there. Like there's no charge in there, there's no Q in there. So really all I have is an electric field, electric potential, and that is it. There's nothing else going on. So let's put a charge in here. Okay, let's put a gold proton in here. You could have a proton in there. Of course, the proton would go with the field this way. Okay, put the electron in there. The electron would go the opposite way. But we'll just stick with a proton for now. So once I've put a proton in there, now we can do the similar type of stuff that you guys have done before. We can start by just, finding the F equals QE. So we could find the force on the proton. So we have the electric field, that hasn't changed. We multiply that by the charge of a proton, which you guys have been using for a while already. And we get about 2.73 times 10 to the negative 13 newtons. Okay, I'm just going to move that over just a little bit so we have more room later on. There we go. Okay. Well, I've got the force. Now what you guys would do last year a lot is you guys would find the acceleration. So we'll just take the force. We'll divide that by the mass of the proton. So we divide the two out. And we get an acceleration of around 1.63 times 10 to the 14 meters per second squared. And now you can do it a couple different ways. I mean, you could do the VAT type thing, but you don't have time. You could try to do it that way. There's different things, but now this is where some of the other expressions could kick in. You could try and use this one to find the time. That would work okay. But the other one that kicks in nicely is we can also use the other major kinematics expression you guys took this year, and that's the V2 squared equals V1 squared plus 2AD, because I have acceleration, I've got distance, and I'm looking for speed. And of course, V1 is equal to 0. So I can easily just go, V2 squared is going to be equal to 2AD because V1 was equal to 0, and I can use this to solve for my speed on the other side. So I can solve for my speed. I've got my 2, obviously. I found the acceleration, and I've got the distance, so that can work really, really nicely. So we put in there, don't forget to square root it, and you will have your final V. And we should get 1.05 times 10 to the 6 meters per second, so something like that. Okay, so that's doing it the very grade 11-ish way, except with low grade 12 kinematics in there. Some people like to do it this way. So now let's do the exact same question with energies, working energies. Do the exact same question. So for this one, I know it's a proton inside of the thing. I don't actually need to find the electric field first, because I can find my energy is equal to QV right at the beginning. And I can find out how much potential energy it has, how much work is going to be done, how much kinetic energy it's going to have by going straight across. So if you do that, you can do the charge times the voltage, which makes it a little bit quicker. So you got the 1.6 to negative 19, and we just times that by the 5800, and we get about 9.28 times 10 to the negative 16 joules. Well, that's the work that was done. That's the potential energy, blah, blah, blah. So this, of course, is also going to be equal to the kinetic energy. And then you can solve for the V that way. So you just have to, double that and divide it by the mass of the proton. And then once again, don't forget to square root. And we should end up with the exact same answer of 1.05 times 10 to the 6 meters per second. So you get the exact same thing. The energy solution is actually a lot quicker for something like this, and that's why energies can be really, really handy. But some people like to do it sort of the forces, kinematics type way. Some people like the energy way. I like the energy way. It really depends on personal preference a lot of the time, but often the energy is a lot quicker. Okay, so this is basically what we've been working on with your parallel plates. So you can actually go back to a lot of the questions you guys have done in grade 11, as well as with the grade 11 review that we did, and we used F equals QE, VAT, basic kinematics. You could actually probably redo most of them in energies, and your answers should all match up pretty nicely.